number 16. And today we're going to answer the question, how can you calculate the voltage generated on a piezo bender, eudomorph or biomorph or whatever you want. I'm going to show a general kind of technique with FEA. And the reason I sort of started down the FEA route is because, well, you're going to have to do a little bit of calculations in order to determine, well, the flexural stiffness, the displacement from a bender. There's a couple of calculation steps. It's not as simple as seeing a simple model. So using FEA will allow you to get make your calculations one step simpler. That's pretty useful as well for both double checking the piezo part of your analysis, assuming your static stress and your application of stress is going to or force is going to be you're fairly confident in that part of your model, but the calculation of voltage, sometimes some FEA models don't have the ability to calculate voltage, and in general we'd like another way to verify that our piezo equations and our material properties are all being transferred and worked out correctly. So in this case we're going to use FEA to calculate stresses on a piezo bender, and then we're going to use our brain. That thing up here, yep, you still got it. Even though you have calculators, you have FEA tools, you have simulations, you have things to measure, you still need the brain in order to calculate voltage. So we're gonna go through that. So real quick, this is gonna be a really practical video. So we have here a 10 by 50 by 100 millimeter piezo element. So the piezo element is bonded to a steel substrate in a cantilever format. We're fixing this side, we're going to be applying a force on the other end. So here are our material properties. So this is one of the cool parts I'm going to show you, calculating the relevant material properties, because actually the specific FEA tool I'm using only uses isotropic material properties. So this is going to be a little bit interesting to allow us to get a good understanding of what voltages we should expect before perhaps creating your device. So what's the modulus of PZT that you need to put in this case? And we're using the piezo as a sensor. In this operation, we're applying a force and we're measuring voltage generated. So here we have the Young's modulus, which is equal in the open circuit configuration, with the superscript D, constant electric displacement, and that's equal to the short circuit compliance, which is usually the one that's reported. So you got to be careful here and use the right compliance value. So the short circuit compliance, divided by 1 minus K31 squared equals the open circuit compliance. So the open circuit the open circuit modulus, which is actually higher than the short circuit modulus. So if you do this equation right here, you plug in the values, you get 87 gigapascals for the value for PZT. In steel, fairly well known, we could just choose a run-of-the-number steel, have it 210 gigapascals, and this is our model. We're applying 10 newtons of force. We have a PZT layer on top and a steel layer on the bottom. This is what we're doing. It doesn't matter if you apply forces up or down. We're clamped in the back. Up or down doesn't matter because, well, this is a linear model. It's going to work well both ways. So here's that model again. I isolated the normal stresses in the X direction. That's what I'm going to be using to calculate voltage. We're making an assumption here, and we're assuming that the voltage generated on the piezo is mainly dominated by the forces developed in the length direction, because as you push down on the piezo, it's going to be stretching in the direction that you are in the transverse direction here, due to the curvature developed from the forces of flexural force applied. So we want to find out the average stress, and that's going to be quite critical to determine the average stress of the device in order to calculate voltages. So we have on these two ends of the piezo negative 0.12 megapascals, and that's the reactionary force, and we also have on the bottom negative 0.14 megapascal. So we take the average of those two and we divide it by the average at the other side, which is basically 0 because it's a free end. So there's no curvature there, therefore there's no stresses due to there's no stresses in the X direction. So this is Z and this is X. So let's then calculate the average stress. So we found that 0.13 megapascals was the average stress on the fixed end. We divide that by 2, assuming we're going linearly down to 0 as we reach the free end, and that's 0.065 megapascals. So we calculate the average stress. Now for the media equation, we have the voltage equals the G31 constant, which is the D31 divided by the permittivity in the 3 direction. So the typical permittivity that we measure for capacitance. So the G31 multiplied by stress, multiplied by area, that makes force, divided by the thickness. So also, since the area is a cross-sectional area here, so then there's the width times the thickness. So then the thickness is drop out here. So we lose that thickness, so we just have width. We carry on these equations, the G31 constant, 25 e to the minus 3, the stress, 0.065 e to the 6 megapascals. So, and then the width, which is 50 millimeters, gives us 81 volts. So here was something really happened, which was quite powerful. We use our knowledge of piezoelectric materials and the basic equations in order to calculate voltages. That now we can understand how much forces and voltages that we expect in our piezoelectric device. And again, one of the reasons why piezo benders generate so much voltage in comparison to a uniformly pressing on a piezoelectric element is because we're operating in a different force displacement mechanism. So if we just think, kind of simply put, very, very simply, kind of some assumption that, okay, the energy we impart to our piezo is related to the voltage generated. Now, there's lots of caveats here, but if you think that the energy that you input to your piezo is equal to the voltage generated, you'll note that force times displacement equals that energy or that work that you do. So typically for our piezo elements or for real world applications, we have the ability to apply forces in a large at a large amplitude. So if you put a weight on top of something, that weight can keep sinking and sinking and sinking. That displacement can be quite large, but the force is rather small. So given the fact that in natural circumstances we have things that can exhibit a long stroke length. This takes you have something with gravity potential energy and it's kind of moving down a bender. We have a large ability to provide displacement, but we don't have a lot of force, and that's typically what we have in the real world circumstance. So by applying that force over a large distance, but basically just letting it droop down and having a small force, we're actually able to import a lot more energy than if we would have a small force, which would only move that piezo, which is going to be stiffer if you just press it uniformly, basically in the thickness or the bulk, you could say bulk direction, the longitudinal bulk direction, and that is going to displace significantly less, and it's going to end up doing a lot less work. For the similar reason, piezo benders are used in ultrasonic acoustic emitters. The reason being that they provide a lot of displacement. We don't want a lot of force when we're trying to move air. Air is very low force, but we need a lot of amplitude in order to push a lot of air. Hence, acoustic emitters are used that have bending format. The most typical one has a very small bimorph, operates at 40 kilohertz, and they put a cone on top, and that creates the acoustic wave at 40 kilohertz used for distance sensing and range finding. So I hope this explanation helped, especially the FEA calculations. They work quite well for understanding and in doing these calculations. Whether or not you have an FEA program that you can calculate voltages from, it's useful to do these calculations both to verify you're doing your piezo implementation properly, because there's ways to do it incorrectly. And additionally, if you don't have access to such a program, you will be able, there's many probably free programs or very inexpensive simulators from like SolidWorks, or what I used was actually Fusion 360 to do the simulation. You'd then still be able to calculate voltages, so you would have some idea of how your device would operate. Now there are realistic differences between your sample and the calculations and experiments. So all those differences aside, you at least have a ballpark answer as to what voltages you expect. So my name is Dr. Shakani. You have been watching the 16th episode of the Shock Show. Look in the description below for a link to sign up for updates on these episodes as they come out. You'll also get the description. You'll get these notes here. So that's kind of nice to have that in your email when those come out to see if this video is going to be an interesting find. And also, please give comments with your questions of new topics or questions on this topic. I'll be sure to get to them. And also, I run a consulting company called Ultrasonic Advisor, so feel free to check out that website, and my services and also my prices are there as well. So keep my engine going and keep these videos coming. So thanks for watching, and I'll see you tomorrow on the 17th episode of The Shock Show.